Good morning. This is Jim Barriman. I'm going to speak to you this morning about model rocket stability and how to calculate it. It's been, I guess, 4 years since I started talking to NARCON about this topic, and it's very exciting to help work with folks to understand this somewhat strange and difficult problem that we all face when we're flying our rockets. I'm going to put up some charts, and we'll talk to what it's all about. So model rocket stability is very important. It's something that needs to be dealt with every time you fly a rocket. Key thing about stability is that it provides safety. And you can predict where the rocket's going to go, or at least as far as the general direction. You're not going to be running someplace where you don't want it to. And finally, and most interesting for competition is you get really good performance when you have a stable rocket. So that, to me, is the equation that's most important in this whole discussion. Now, stability is, in a simple sense, just the ability of a device to return to a neutral position when it's been displaced. I like to use a bowl with a ball in it as an example. Stable motion for such a device where you have a ball displaced up the side of a bowl is that a stable situation is the ball will roll back down into the center of the bowl, and that's about as simple as it gets. On the other hand, turn the bowl over, put the ball on top. Well, you can't, because it's going to roll off and bounce away in some direction, you don't know which one, and that's a classic unstable motion. Neutrally stable, and that's the third form of stability, is where it's on a flat plane, and no matter where you put it on the flat plane, it's going to stay there, and that's neutrally stable. It's the same as stable, but there's no motion involved at all necessarily. So for a rocket, and that's what we're talking about here, stability has to do with the airflow over the rocket and where the rocket's pointing. So similar to the ball in a bowl, you look at the rocket flowing through the air, flying through the air flowing over it. You displace it relative to the air to an angle of attack. And a stable rocket will tend to work its way back to a zero angle of attack, which is the same as being at the bottom of the bowl for the ball. An unstable rocket, well, you don't know. It's going to go just about anywhere, and of course, that's not a good thing. That's a bad thing. Neutrally stable is actually when you could displace a rocket and it stays in the same orientation relative to the airflow. Those are hard to find, and I'd love to see one someday, but I haven't yet. They're all very dynamic. Thank heavens, that's one of the joys of rocketry. What does it look like from the ground? Well, stable rocket, you can see a few wriggles maybe, but it generally flies up the way you want it to. Unstable, Katie bar the door. You don't know where it's going to go, and that's a very bad thing. It's unsafe, and it's not at all why we fly rockets. Neutrally stable, well, I'm guessing that's what one would look like. Frankly, like as I said before, I've never really seen a neutrally stable rocket, but I assume they're possible. Now, when you talk about a rocket flying in any fashion, there's three forces acting on it. They're translational forces, that is, those that cause it to move or try not to move. Of course, the most important one for getting it to move is the thrust. Um, the weight is going to be there no matter opposing the thrust. And the drag, once you got it moving, the drag is going to be resisting its motion as well. So going straight up, of course, it's a no-brainer. It looks pretty straightforward. On the other hand, if you're looking at it at an angle to the vertical, the weight will be trying to pull it down. Thrust and drag are still opposing each other. It turns out the drag, like any aerodynamic force, increases by the square of the velocity. So the more thrust you have, the more four times the amount of drag is induced depending on the velocity. But the key point that you can see here is the center of gravity is where all these forces are acting. So let's talk about that center of gravity. It is a special place. Again, all translational forces act through the center of gravity, but we're really not talking about its translation. We're assuming it's moving. What we're really talking about is how it rotates. That is really your key to stability. It's how that rocket rotates. And the key to the stability and understanding is that it always rotates around the center of gravity. You can show this for yourself. I mean, you can use a stick like this shows. What I like to use is a broomstick because it's not uniformly weighted. But you can grab that at one end and try and rotate the broomstick, and it's kind of hard. You grab it by the center of gravity, you move up the broomstick to where it balances with the broom and the stick, and by golly, it's a lot easier to rotate it. And that's the center of gravity, and that's why you'll see for yourself that things that are rotating tend to rotate and will always rotate around their center of gravity. And so that's a very important part of our discussion of stability. But the other part of stability is the fact that it's all about aerodynamics. The forces on the rocket that are rotational tend to be aerodynamic forces. These come from the wind. They come from the fact that anytime it goes to an angle of attack relative to the airflow, there's going to be pressure forces on the side of the rocket that tend to influence and strongly influence how it flies. Well, let's assume for the moment that it's a stable rocket. And so you can see that as you add up all these forces, air pressure forces on the side of the rocket, you can actually create a single force, add them all up into a single force that acts at the center of pressure of the rocket, and that's why that's important, and creates a normal force that's, as its name implies, is normal to the axis of the rocket. So together, they form a moment. A moment is nothing more than a force acting at a distance from a given axis of rotation. Well, of course, the axis of rotation for a rocket is the center of gravity. And the moment arm is the distance between the center of pressure and the center of gravity. So it's a moment, and we depict a moment with an arc of a circle showing that it's tending to rotate the rocket. And so you're at an angle of attack. You're going to have an aerodynamic moment. And yes, it could be stable, like this one shows, or it could be unstable, which you'd really rather avoid. So here we look at a stable rocket with the center of pressure behind the center of gravity, and that's where the whole concept of making sure your center of pressure is behind your center of gravity. Because if it's ahead of your center of gravity, you can see that the normal force would be tending to open up that angle of attack, and now your rocket is going someplace that you have no idea where it's going to go. Not a good situation. Now, we want to have a rocket that's stable, but we do not want it to be too stable. And the reason is, the major force acting on a rocket when it's flying, external force outside of its own drag, the thrust, and its weight, is the winds. And you have a wind acting on a very stable rocket, and it's going to tend to go into the wind more because the stabilizing moment that is caused by the forces on the sides of the rocket are tending to push it into the wind, and it's going to arc over sooner than for a nominally stable rocket. So Tom is going to talk about this later on, a little bit more detail, but key concept to get good performance is to have a stable rocket, but not too stable. Typically, we like to say about 1 caliber. This is actually on the order of 2 calibers shown here, but on the order of a caliber of stability, that is the distance between the center of gravity and the center of pressure, on the order of the largest diameter of the rocket. Now, of course, you've got to determine what your stability is. It can be a challenge. For those designs that are already built, it's pretty straightforward. You can do a swing test, which is basically tying a string around the center of gravity tightly, and swinging the rocket literally around your head. To me, that's I've done that many times, but you got to do it with a rocket that you've already built. It doesn't do you much good at all to deal with a new design that you're trying to put together. You can't use it on unbuilt designs yet. So you've got to figure where is the center of gravity on your design, and where is the center of pressure. Center of gravity is fairly straightforward. You can weigh each of the components of your rocket and determine by balancing them with a string or whatever where they're at. Many of the design programs that are available will provide you with that information, so you can actually cobble together a rocket design from known components, and it will tell you what the design programs can tell you what the center of gravity is. That's the easiest way to do it, but if you don't have that, most of us do now these days, but if you don't, you can determine the center of gravity by just working with the various components of the design that you want to build. Center of pressure is a different breed of cat. The cardboard cutout method is a classic method to determine the center of pressure. The problem with it, and the cardboard cutout method really comes down to taking a shadow, basically a sideways view of your rocket, and tracing that out on a piece of cardboard, literally cutting out that flat piece of cardboard, finding its center of gravity. And that turns out to be the center of pressure at 90 degrees. That is, when the rocket is flying sideways. Well, you don't fly sideways if you're building a rocket that you want to go straight up. So that's really going to make a rocket that's way too stable, and it's not a good way to do it. But that was the only way for many years. Then a while back, I came up with some work that I was doing for NASA, and I'll talk about that later, that allowed me to put together a series of simplified equations that you can use to actually calculate the center of pressure of a rocket using aerodynamics. And those equations are now available pretty generally. They're certainly published in the Handbook of Model Rocketry. Harry Stein, when I first, back in NARM 8, showed off the equations that I had derived and actually flew a couple of rockets, was excited enough about having that kind of capability that he had published it in his Handbook of Model Rocketry. The generally available, there's lots of different places on the web where you can find them, but the most useful ways to apply them is using either RockSim or OpenRocket that have the equations incorporated into them. Let me talk a little bit about the equations. I'm not going to spend a lot of time or a lot of detail on the equations. They're generally available and are fairly straightforward to utilize. So once I get my mouse working right, basically I derived them as part of my work for sounding rockets with NASA. We're flying lots of aerodynamically stabilized rockets, just like sounding rockets, only bigger. We did not have until fairly recently, within the last during this current century, or current century, rockets or sounding rockets that had anything other than aerodynamic stability. I was using based on my experience with both in school and at work, engineering and research that had been done by the NACA, the precursor to NASA. They'd done a lot of wind tunnel work, a lot of theoretical aerodynamic derivations, but they'd never been really applied in a direct, straightforward sense to calculating the aerodynamics of a sounding rocket. What was necessary to do that was some pretty significant computer capability. These days, probably your home PC would be adequate, but it would be still a significant computer programming job. Matter of fact, you'll be hearing a little something about that in the discussion of the parachute, the program that's out of Florida that's looking to fly rockets to test new parachute designs. They use some of those same equations for their work, but they're too complex for the average model rocketeer. So I was able to make some appropriate assumptions and simplify them down to what was fairly straightforward algebraic equations, and did not really require a lot of computer capability. You could do it on a calculator if you wanted to. Now, these assumptions, there's a lot of them, but really there's a couple of key ones. The rigid body is very important. Axially symmetric, that is, that it's the same all the way around. It's got 4 fins or 3 fins. It's not something that's like a space shuttle that is different in different directions. The nose tip has to come to a point, and that's simply because it needs to, the way you integrate the airflow. Fins are thin, flat plates. Actually, they're not, but they're close enough that it does the job. Key one is the low angle of attack. If you get to angles of attack beyond 10 degrees, you're starting to impose nonlinear aerodynamics on the rocket. And that is the equations that I derived can't handle that, unfortunately. But it doesn't matter too much because, amazingly enough, 99% or 99.9% of our rockets are flying at less than 10 degrees, even right off the tip of the launch rod. And if they get above 10 degrees, they're pretty well past that point as they accelerate fairly quickly. The flow around the rocket is potential flow, and that's a technical term, which basically says it's smooth. There's not a lot of turbulence, vortices, or friction that is impacting the flow over the rocket. Now, the friction part is what yields mostly the drag, and so that's acting along the surface of the rocket, along the axis of the rocket. So even though there is friction, it doesn't impact the stability situation. The flow is subsonic. That's crucial. Again, much of the work that you'll hear about with the project that's working on parachutes, rockets to test new parachutes, is supersonic. So they have a different problem, and they've had to deal with the full set of equations. And the flow is steady state. That it is, again, not a lot of well, I'm trying to think about that. Steady state is really that it's happening. Anything that's happening is relatively slowly as the rocket moves through the, and relative, we're talking tenths of a second level variance, which is not the case with model rockets. So when you go after the equations and understand what the basic nature of aerodynamics are, you come to terms with aerodynamic coefficients. And aerodynamic coefficients have a key aspect that make them actually a very good thing to use. If you look at the normal force on a rocket, there's three things not associated with the rocket itself, per se, that impact the normal force. The density of the air that it's flying through, of course, it could be flying through water, and it'd be a lot more dense, and you wouldn't be going very far. The velocity of the rocket through the air, and last but not least, your angle of attack to the airflow. Those are the three key external factors impacting the stability and the aerodynamics of a rocket. There are two inherent factors, though. The size of the rocket, that is, a bigger rocket will have larger forces acting on it, but relative to the shape of the rocket, this is the normal force coefficient that defines, or that is a function of the shape of the rocket, is the only thing that depends on the shape of the rocket itself. So when you put those together in an equation, the normal force is a function of the shape of the rocket, the velocity and the density of the air. That term in parentheses is called the dynamic pressure, and that was derived again through wind tunnel testing and that sort of thing, and of course through theoretical calculations. But they use that 1/2 rho v squared as the dynamic pressure, and they determine that it is that value by instrumentation in wind tunnels. So they know that's the dynamic pressure acting on a rocket due to the airflow. And then, of course, the fact that it's at an angle of attack and the size of the rocket. Again, a smaller rocket will have smaller forces for the same velocity and the same air pressure and the same angle of attack. So since the Cn alpha, or the normal force derivative relative to angle of attack, this is the factor that depends only on the shape of the rocket. And that is why we use that to calculate the center of pressure. Similarly, there's another one, and you'll see it in a second, the aerodynamic moment coefficient. So remember the normal force acting at the distance from the center of gravity creates an aerodynamic moment about the center of gravity. And so the center of gravity and the center and the moment coefficient and the normal force coefficient are the two key aspects of calculating the center of gravity, or center of pressure, I'm sorry. And when you do that, the other key aspect of the equations is the fact that you can do them, like with center of gravity, you can do them by regions of the rocket. In other words, you can break the rocket down into pieces and calculate the information, the characteristics of those pieces, and then put them back together and create a result for the entire rocket. It doesn't necessarily have to be that way in general, but it is. It turns out, very fortunately, that both for center of gravity and center of pressure, you can break a rocket down into its component pieces and just calculate the information for those pieces. One of the things that people will find out as they look at center of pressure is that the cylindrical bodies, because of the low angle of attack, cylindrical bodies do space things out, but they don't contribute that much to the center of pressure of the rocket, again, simply because it's at such a low angle of attack. But the fact that the nose cone and the shoulders and the fins are more affected by the fact that it's at an angle of attack, those are the components that really you need to concentrate on. Well, I'm going to talk only about one component, and that's the center of pressure of the nose. The reason I'm doing that is because it's the first thing you deal with, the nose of the rocket. Second of all, it's one of the simpler ones to deal with. And so I can put up some fairly complex looking equations, but they turn out to be not so complex. So the center of pressure is a function of the size of the rocket here in terms of the diameter of the rocket. And typically if we have multiple diameters, we use the largest. And then it's a ratio of the Cm alpha, the moment coefficient, divided by the normal force derivative, the moment derivative divided by the normal force derivative, and you turn that into some equations, more complex. Again, the Cm alpha is the derivative, and this is a little bit of calculus creeping under the tent here, but near alpha equals 0, it's basically the slope of the normal the moment coefficient. Similarly, the Cn alpha is the slope of the normal force coefficient, near angle of attack of 0. So you have to go ahead and integrate that is, add it all up along the length of the rocket, or the length of the nose cone in this case. And it turns out the CN alpha of a nose for all nose shapes, any shape that you can come up with that is meets all the assumptions and varies smoothly, you get a normal force coefficient slope of 2. That's a great result. Similarly, you do the calculus on the moment coefficient, and turns out that the center of pressure for the nose is basically a function of its volume. So you have all these different shapes. You've got cones, you've got spheres, you've got ogives, which are the probably one of the most common shapes for a model rocket. As an ogive nose, which is an arc of a circle that then is tangent to the body at the back end of the arc and comes to a point, and then is rotated to form the ogive nose shape. And an elliptical nose, all of them end up with the same equation, simply because it's a function of the volume. The length is a function of the size. The nose area at the base of the nose is a function of the size, and the volume is a function of the size. But they all combine together, and that gives you the center of pressure. Now, you talk about a cone. The center of pressure is about 2/3 the way back of a cone. It's 2/3 the distance. So again, that yields a fairly simple result for a cone. For a parabola, it's halfway back. For an ellipse, it's about 1/3 of the way back. Those are fairly simple results that you can calculate, and the number is a simple fraction. But there is one shape that was a challenge. That was what we call the tangent ogive. Okay, the tangent ogive is again an arc of the circle. It goes to a point at one end and goes to the parallel or tangent to the body tube at the back end. So it flows smoothly in. The flow comes smoothly into the body, and then when you rotate to form a nose cone, it's a pointed shape, and we all use them. We've all seen them one time or another, whether or not we knew that's exactly what they were. But when you go to calculate the center of pressure of that beast, wow, that equation up top tells you that it's pretty complex. But when you actually go to calculate it, now I used a computer to do this, and you could do it. You could try cranking out that equation yourself. You'll find out that lo and behold, as you get above a certain size, that it's linear, and you can actually compute the slope, and it turns out to be 0.466, and so you can use that, and that's what I provide in those equations. But when I first looked at that equation, I said, oh my gosh, I'm not going to be able to make this simple in any way, shape, or form. But nature came through for me. We actually can do it. Typically, nose cones have an L over D of like 4, somewhere between 3 and 4, or maybe 5. So you can see it's nice and linear in that area. So we can use this 0.466 and be comfortable that we're going to get a good result. So that's just a touch on the various techniques that I used in putting together the equations that were simplified and usable. Again, they're available in the handbook and lots of other places on the web and in the buried in the RockSim and in OpenRocket. These equations have been around a while now, over 50 years. Um, I, when I first arrived them, I did some comparisons with sounding rocket wind tunnel data and was assured that they were good. I've test flew a number of rockets, including the Century Javelin, which is depicted here. And you can see what happened with the Javelin. If you're using the cardboard cutout method, you'd think it was a lot more stable than it is. But in fact, once you put an engine in the back and you have the rocket's actual CP location, it's quite far back. It's right at kind of just at the front end of the fins. And of course, as the rocket burns, as the motor burns, the center of gravity changes. So it actually it becomes more stable as the center of gravity moves forward. So you've got a lot of experience over 50 years, and a lot of people have used it to make sure that their birds are going to fly well and fly high. So are you stable? Well, again, stable leads to safety, leads to predictability, leads to good performance. But you want to know it before you fly it, and that's the way you should be dealing with the center of pressure and the stability of your rockets. I'm happy to take any questions that may have arisen. I'm going to stop sharing the charts, and we'll have a chance to maybe interact a little bit. I see we do have some questions. Well, let's see. The question is what other extensions or applications of the barium equations have I encountered? I think it usually has to do with nose shape, and people trying to apply it to unusual fin configurations. And it's all a question of using your common sense when you do that. I guess the first thing I encountered, of course, things like the Mercury capsule, the Apollo tower on the front of Apollo missions posed a little bit of a problem, but really they're a small part of the overall rocket, so they were pretty good to deal with. I haven't really run into too many oddball people trying to apply them incorrectly. I think we've been pretty lucky in that regard. Short, stubby rockets is a good question. I I think they would apply even to really short, stubby rockets because the fins tend to be such a major plate there. Oops. Well, I'm sorry you couldn't see my slides. I hope they came up again. I had them shared. Um, Well, from Sibo Van Gool, I really taking the fin equations and getting those into a form that was straightforward to deal with. When I first published them, I published them through Century with a charts that took even the equations, which were relatively simple, and but getting to those simpler fin equations, I think was a particular challenge, but it wasn't that awful. Okay, well, Steve, I'm sorry. I thought I had the charts up. I I don't know why they didn't show up. Let me try again. Um, that should have them up. Let me know if they didn't come up again. I'm not sure why I had a problem with that. That's I have. Bear with me while I try again. Uh, they should be visible at this point, and I'm not sure why they weren't before, but they are there. Steve, can you see them now, or have you given up? Unfortunately, I can't see my slides and your questions at the same time, so I'm off stage. Okay, Tom, I see what you're saying. Aye. Well, folks, I'm showing that they're shared, but I don't know why they're not coming across. I uh, I have shared them with the with Ed and Todd, and so they should be available. Um, Let me try going through the process again. Tom, I hope you have better luck than I have in showing any slides. I'll go through them, or I think I have them up again. Well, I'm stuck. I don't know what else I can do. Any other questions? Why is this? Okay, I'm going to try again. Oh, Sibo, thank you for the kind words. I don't know. Tom, again, I need to answer your question by saying no. It was first applied to full-size rockets, then applied to model rockets. The work I did for NASA was actually for uh, aerodynamics of sounding rockets. But I'm appalled that I wasn't able to get the that this that the charts didn't actually show up. Oh, rascal. I've got it shared. It says you are sharing your screen. I don't. There's a thing that says off stage, and I don't know how to get rid of that. That looks like it came up. Don't know why. Oh, Siba, are you still with me? I don't know. Anybody there that yeah, I feel bad that there was something funny that didn't work. Okay, well, good. I can see him now. I don't know what exactly I did. I just worked through them. Okay, so I did work through the slides anyway, and again, they should be available um, through Todd and Ed. So thanks, folks, for the feedback. Um, don't know why I had a problem because it seemed to work. From my viewpoint, it looked like it was working fine. Yep, I use Google Chrome. Oh well, I think I'll shut down now. We're about over.